The objective of this video is to formalize the boost converter by analyzing its operation and transient waveforms. The purpose of a boost converter is to increase the source voltage to a higher voltage level at the output. That's why it's called a boost converter. You're boosting the voltage. I've drawn on this page our generic single-pole double-throw converter. Keeping in mind that we're trying to boost the voltage from the input to the output, I want you to label the voltage sources as Vin and Vout and indicate the direction of the pole current, whether it's positive or negative. Press pause and press play when you're ready to resume. Alright, you should have labeled the output voltage as being on the left side, Vout. This is your throw voltage. Remember, we've previously talked about the throw voltage and pole voltage relationship of the single pole double throw converter by noting that the pole voltage must always be less than or equal to the throw voltage. We pulse width modulate the pole between the two throws, and so it's impossible for our pole voltage to exceed our throw voltage. Therefore, if we're going to try to increase our source voltage, we must put the output voltage across the throw. Next, since power is going from our source to our load, the pole current must be nominally negative. So In is in this direction, and Iout is in this direction. Keeping these observations in mind, the fact that we have a negative pole current and a positive throw voltage, I want you to sketch the semiconductor realization. If this is hard for you, I strongly suggest you go back and realize our lecture notes on semiconductor switch realization. So press the pause button and press play when you're ready to resume. You should have sketched the following diagram. Note that we've replaced the output voltage source with a resistance and our filter capacitor, similar to how we drew the buck converter. Our power direction is still going this way, and the convention for drawing converters is that power should flow left to right nominally. So I'm going to erase this and resketch it with that convention in mind, putting my input source on the left and my output load on the right. I'm going to denote my inductor current as having the same direction as my input current. So IL will be going left to right, while we keep our sign convention for the description of the pole and throw currents. So that's to say that IL is equal to a negative IP. We'll label our diode current, our capacitor current. So similar to the buck converter, our converter has two fundamental states depending on which position the pole is in. If it's connected to the top throw, then our diode is conducting. If it's connected to the bottom throw, then our MOSFET is conducting. So let's sketch these two states. When our MOSFET is conducting, it appears as a short circuit, and the diode, which would be over here, appears as an open circuit. In state 2, our diode is on and our MOSFET is off, which means that our MOSFET appears as an open circuit and our diode appears as a short circuit. So, similar to the buck converter, we can see how the voltage across the inductor varies to determine its current derivative relationship, whether the current is increasing or decreasing. Let's construct the same table we did in the last lecture. This time, we're going to note that our duty ratio, D, is the duty ratio of the MOSFET, which is the same as the duty ratio of the pole being connected to throw 2. So duty ratio, again, is the on time of the MOSFET divided by the total switching period of the converter, TS. So the total time that we're in state 1, when the MOSFET is on, is going to be D times Ts. By definition, since D is the duty ratio of the MOSFET on time, the time that the MOSFET is on must be D times Ts. The rest of the time, we're assuming that our diode will be turned on, so that we have a total time of 1 minus D times Ts. So we're either in state 1 or in state 2. There's no other state possible, so if we're not in state 1, we must be in state 2. Our drain source voltage of our MOSFET, VDS, is assumed to be 0 volts when our MOSFET is on. Again, realistic MOSFETs are going to have some channel resistance. This would actually be your throw 2 current times your channel resistance, but in this case, let's approximate it as 0 volts. VDS during state 2, when our diode is on, is going to be equal to our output voltage. Our diode voltage blocking requirements can be summarized as follows. In state 1, our diode is off and our MOSFET is on, so the diode must block the entire output voltage. And in state 2, when our MOSFET is off and our diode is on, the diode is assumed to have no voltage drop across it. Realistically, there will be a certain forward voltage drop associated with the device from the manufacturer's datasheet. Our inductor current, or instantaneous inductor current, in state 1 it's going to be equal to Vin, and in state 2 it's going to be equal to Vin minus Vout. So we can note the polarity of this. Vin is positive, so in state 1 our inductor voltage is positive, and since Vout is greater than Vin, in state 2 we have a negative inductor voltage, which means that our inductor current is increasing during state 1 but decreasing during state 2. In all states, our input current is equal to our inductor current. This is a difference from the buck converter. And our capacitor current, which is equal to our diode current minus I out, is going to simply be equal to I out in state 1, but I out plus the inductor current minus I out in state 2. Next, let's do the steady state analysis of the boost converter. And the way we've been conducting the steady state analysis for both the buck and the boost converter harkens back to our previous discussion about stiffness sources for single pole double throw switch converters. And in that lecture, we talked about the need to assume that our currents are always we have a constant pole current, or rather than a constant pole current, a continuous pole current, that our pole current never goes to 0. This is referred to as continuous conduction mode. So all of this analysis assumes continuous conduction mode, that our inductor current never goes to 0. Well, in a couple of lectures, we were going to talk about discontinuous conduction mode, where we allow our inductor current to go to 0. So for now, just keep in mind that the analysis that we've been considering so far pertains to the case where we have sufficient stiffness for our pole current. That is, our inductor current does not go to 0. Note that the input voltage of the converter is equal to the average pole voltage of the converter. You can see this by inspecting the single pole double throw converter diagram that we drew at the beginning. I want you to relate this, that is the input voltage of the converter. I want you to relate the input voltage of the converter to the duty ratio of the converter and the converter's output voltage. Recall that the duty ratio, we defined it previously as being the duty ratio of the MOSFET. That's the time that the MOSFET is on over the switching interval, or in other words, state 1. So take a second now, pause the video, and complete the expression that I started here. Vn is equal to some function of the duty ratio times the output voltage. Press play when you're ready to resume. Again, so when our MOSFET is on, or during state 1, which occurs for d% of the interval, our pole is connected to the bottom throw. When our MOSFET is off, our diode is on, and that occurs for 1 minus d% of the interval, When the diode is on, the pole is connected to the top throw. So therefore, the average of our pole voltage must clearly be equal to 1 minus D times our output voltage. And we can rewrite this expression to solve for V out as being equal to V in over 1 minus D. So solving this expression, you can solve this expression for the duty ratio of the converter for a specified input and output voltage combination. Next, we can relate our output current to our throw 1 current as being the negative of it, and we can make a similar argument for the average output current being related to the average input current by 1 minus D. So when the pole is connected to the top throw for a 1 minus D amount of time, our output current is instantaneously equal to our input current, and therefore the average is 1 minus D times the input current. This happens to be the average diode current, or the average of ID. Next, we can solve for our throw 2 current, the average of our throw 2 current, to determine the average current through our MOSFET, which using a similar argument is going to be equal to D times our pole current, which is just negative D times IN. We can also relate our average inductor current to IN as actually being identical, since the input current is always flowing through the inductor. This is a key difference from the buck converter. Now, our inductor current must carry the average of our input current, and is something that is used for sizing the converter's inductor. So we care about all of these quantities that I'm highlighting because they're key for dimensioning the components that we populate our converter with. We care about the required breakdown voltage of the diode and the MOSFET, as well as the average, or in most cases RMS current, through our MOSFET and diode and inductor. Next, let's sketch the transient waveforms for this converter. We'll start by sketching the sawtooth carrier that we've been previously considering. And as you recall, the sawtooth carrier is actually what we use to determine the instantaneous value of our switch, whether our switch is on or whether our switch is off. And as we've discussed previously, our carrier has the same fundamental frequency as our switching frequency. Let's assume that we have a duty ratio as I'm showing here. Just give us the following on switch state. And so next, if we sketch Q, where Q is either 1 or 0, indicating whether our MOSFET is on or off. And if you recall, the rule is that when D is greater than our carrier, Q is on, our MOSFET is on, and when D is less than our carrier, our MOSFET is off. So you can see that during this time right here, our MOSFET is going to be on. And when our MOSFET is on, by definition, we are in state 1, which means that we can sketch our inductor current as being equal to our input voltage. When our MOSFET is off, we are in state 2, so this means state 1, 2, 1, 2. And when we're in state 2, our inductor current is equal to our input voltage minus our output voltage. And our inductor current has an average value equal to the average of our input current. And in state 1, the inductor current is increasing. And so we visualize our inductor current as consisting of an average value, IL, and then a ripple component, delta IL, where similar to the buck converter, we can calculate that ripple component by either integrating this region right here of the inductor voltage, or this region. And we solve this by using the differential equation that governs an inductor voltage and current behavior, which is that V is equal to L di dt. And we get the following expression. Next, let's sketch our diode current. The diode is off in state 1, but it turns on in state 2 and must instantly carry the inductor current. And this allows us to sketch the capacitor current, IC, which is equal to our diode current minus our output current. And the same observation holds as we've previously made, which is that the area in this region, the total charge flowing into our capacitor, must equal the total charge flowing out. So the area of these two regions must be equal. The net Q is equal to 0. And similarly for our inductor voltage, the area of region A and region B must be equal. And this again is used to, we can use this relationship to ensure that our converter remains in steady state, that the output voltage is not walking off to positive or negative infinity, and similarly with the inductor current. We can use our capacitor current waveform to then calculate the ripple in the voltage output, like we did for the buck converter. But we will not do that in this lecture.